context, this was actually a surprisingly challenging talk for me to put together, given the format here. And sort of the tutorial I gave on Monday, and then having most of my close collaborators at this meeting. Also talking, which means I can't pirate any of their slides. And so I definitely want to give co-author credit to my companions for dinner last night, because I was a bit stumped on where to go, but some very helpful, constructive feedback reminded me that in general, scientists like hearing a story and the backstory behind how things come about, and realizing that while I've been working with this material for a decade, it's still new to many, if not most people. So dating myself in time and culture, the title here is a reference to a movie from the 90s, Four Weddings and a Funeral, not just for the structure of the title, but the thread that came together as of about 10:30 last night was so in that movie, it starts off with 4 different stories that seem to not interact, and then sort of in this sort of style of movie making where you find out the connections as the thing goes on. And so I want to tell you some stories about BTC&E, how it works, how we've developed the system, and sort of pull out a thread that I think unites these. So just because we've had some turnover and we've had lots of talks, start off just to refresh. Why am I talking about this material? And even the name of it is already, in the chemical formula there, you can see it's already atypical. It's vanadium complexed or coordinated with tetracyanoethylene. So it's basically a binary solid where instead of 2 atoms, your second atom is a small molecule. That's pretty exotic system. And so why are we bothering? And so again, somewhat historically, not quite this plot, but one very similar to it is the reason my group stuck with this. So we originally started working with this system when I started at Ohio State, collaborating with Art Epstein, who's one of the 2 people who really drove its development. And this was in 2006, 2007. So spintronics was still a thing. So the first thing we tried to do with VTC&E was turn it into a spin injector, which works, but not well enough to really justify a long-standing investment. And we were playing around trying to understand the magnetic properties, and FMR has a long history at OSU, so there's a lot of expertise and facilities for looking at that. We're like, well, let's see what the FMR tells us. And we came up with this completely shocking result. And the order of operations here is important because BTC&E is relatively new at the time, and in a lot of ways still new. I mean, one of the dirty secrets of the materials that underpin all of solid state science is that developing an understanding of any material system takes either a lot of person hours, let's say, which a few people and a lot of time on the calendar, or a really large effort if you want to compress that. So we started with this, which is this remarkably narrow line width. I apologize, you can't really see here, but that peak to peak line width is about a Gauss. And it's a longer story that I'll tell over coffee about how we even realized that that's an impressive number, because we're not an FMR group. Once we did the comparison, realized how close that is to YIG, and then did the frequency measurement to extract this parameter alpha, which Greg talked about some yesterday, and I think we'll hear more about today. We realized it's really got these remarkable properties, but we didn't really know why or how. And I spent probably a decade talking about this system, where the first question was always, what's the crystal structure? What's the electronic structure? And I'd say, well, it's kind of like this, but we have a lot of open questions. In my tutorial, I laid out how we, I think, have answered those questions. But the bottom line is, and this is meant sort of as a motivational slide, is that whether you care most about the damping or most about the absolute line width, this is a system that's competitive with YIG on both metrics. And I don't think there needs to be a winner in this kind of thing. Both materials have their strengths and weaknesses. The thing that's remarkable to me as a scientist is this doubles the number of materials that are suitable for sort of high quality magnonics. And it's not like there hasn't been work in this area, right? YIG has been critical for 5 decades or more. So this is a really hard problem that we kind of stumbled across. So our understanding of this system started with pushing towards applications. And so we started collaborating with Greg quite some time ago for the quantum magnonics pieces before really understanding how the material was working. So those things have been proceeding in parallel. So I want to take a step back and talk a little bit about how we produce this. So it's a chemical vapor deposition reaction, and this diagram at the top is just basically a glass tube furnace that lives inside of a glove box because the material is air sensitive. So we need to be a little bit careful about how we handle it. We just flow in argon from the ends, not pictured here. There's a pumping port in the middle. So that provides the gas flow that provides the mass transport. Then on the left side, we have TC&E, which maintains its molecular character, whether it's an isolated molecule or part of the solid. And that is just a solid powder that we sublimate in the feed tube. That's what that blue rectangle on the left represents. The vanadium precursor is where we separate the bold from the meek, because finding a precursor to hold the metal is challenging. And here this is vanadium hexacarbonyl, VCO6. So that sits in actually a T-junction. So there's and it's a liquid at room temperature. So we flow air over. In fact, we don't need to heat this, we need to cool it because the vapor pressure is so high. These two things come through and they react in that green zone, depositing on the walls of the chamber, and if you put a wafer in there, your substrate. So none of this is sort of unique. This is, many CVD reactions run this way, but it's useful to give some context of when we're depositing materials. This is what we're doing, and that green zone kind of gives you a feel for sort of the region of uniform deposition that we can achieve. It's also worth looking at what this looks like in real life. So this glove box on the right is where the first version of this reactor lives. We now have a second version with better control and stability that lives in a different lab. Over here, you can see half of the fume hoods that we use for this synthesis. There's another 2 fume hoods over here, but even with panoramic mode on your cell phone, that was hard to get. And this just kind of underlines, I've been talking about this for a while. Why have more people not just jumped in on this, given the selection pressures on magnonic materials? And I absolutely would encourage more people to do this, but the material synthesis has some real barriers. And it's not just that the material itself is air sensitive, it's this VCO6. So this is not commercially available anywhere. And the synthesis requires moving back and forth from what's known as a Schlenk line. I know a little bit of chemistry nomenclature by this point, and I work with the material. So this is real mad scientist looking stuff. If you look carefully, you can see there's like a metal lattice in the back of the fume hood, and we've got like glass vacuum lines and beakers that we plug and unplug, and things that bubble and boil, and witches' cauldrons and whatnot. And so the entire VCO6 synthesis is air sensitive. And the reason why my lab looks this way is because we were collaborating with Art Epstein initially on the spintronics work. We'd just seen those really spectacular FMR results, and then Art retired. And so we had a question, we had sort of a challenge of like, okay, so are we going to give up on this material system, or are we going to figure out how to synthesize it on our own? And I have a background from my PhD work in MBE. I was like, well, MBE is hard and materials are materials. How hard could this be, right? We all know how that goes. Fortunately, I inherited Art's last 2 PhD students who knew how to do this synthesis. And so we sort of maintained the chain of institutional knowledge to set this up in my lab and keep it running. And we were doing this for about 2 or 3 years before we got our next round of results, and I started going out and talking about it, including to chemistry conferences. where I learned that every chemist who I talk to basically refuses to do this kind of synthesis in their lab. Like, that's way too hard. It's pyrophoric, which is potentially dangerous. Like, no, we just don't want to bother with that. I was like, oh, so we accidentally leapfrogged to, you know, so we're, one way to, an entertaining way I like to think about it is, you know, I'm training truly world-class synthetic chemists in a needle narrow phase space of chemistry. So anyway, like I said, some stories here. So I just thought that would be fun context for everybody to have about how this comes about. Oh, one last thing. So this is the kind of thing that we like to do in my PhD work in growing thin film is, okay, you have materials growth parameters, and you want to map that phase space out to see where the good growth is at. And this is something I mentioned a bit on Monday, but so all those red dots are samples that were grown. And then the squiggly lines are FMR spectra without any scale, representing the measurements of those samples. But you can just sort of see like the peak structure, right? And you can play a little bit of Where's Waldo for a moment and see, where do you want to grow? You want to grow way out here at the edge of phase space. And so for good crystal growth, generally there's a rule of thumb that you want to grow just colder than the decomposition temperature of the material. So you want to give enough thermal energy for your constituents to move around and find their true equilibrium, not some metastable configuration that's going to give you defects. So you really want to be at the edge of the growth window. And that also historically has been a challenge with this system, because the true sort of chemistry-inspired tube furnace CVD setup isn't really stable enough to maintain that growth condition. It drifts around. So the second generation chamber that we have running now, with a lot more automated control, actually, I'm very proud of the graduate student Donnelly Cormode who built that system, because the very first sample she grew matched that parameter. So it did a really good job with that control there. Okay, so now moving into sort of some of the results I talked about a bit already that have appeared. And this is now going to be a bit ahistorical, jumping around in time, but I'm going to start off with what I would call intentional or designed patterning of magnonic resonators. So that, I mean, a nice thing about magnons as opposed to photons is they can't escape. They're trapped. They're always within your magnetic material. So if you pattern your magnetic material, you have made a resonator. Challenge for VTC&E is that you can't get it very hot. It's air sensitive. And many conventional solvents present in resists and fabrication will actually dissolve the VTC&E. So we had sort of tiered challenges here in figuring out how to pattern this, and we spent a lot of time trying various things. You know, do you put the film down and then try and etch it? We settled on this liftoff approach as the most general. And here you can see there's a bilayer of MMA and PMMA, which is a typical process. And then in this case, we developed a bar, so a trench, cut it in half so you can see the cross section. Then we deposited a layer of alumina to trap, because the solvents in the PMMA are not friendly to VTC&E. So we're minimizing outgassing by sort of capping the resist layer before we deposit the VTC&E. Put it into the tube furnace, deposit everywhere, and then do liftoff. And we spend a lot of time playing around with liftoff. Turns out dichloromethane is a solvent that will attack PMMA and VTC&E. We've since learned, if there are any chemistry aficionados in the audience, pyridine also works pretty well. And we're starting to look at using those solvents for post-growth modification, which is a whole different direction, but just sort of highlighting some of the phase space that opens up with these kinds of systems. So this is the patterning recipe that my student at the time, Andrew Franson, developed. You saw this picture before, you know, some more OSU branding. If you can make any picture you want, you know, you gotta do some brand. But I think this is something that is important to emphasize. So this is adapted from this reference here, and this is highlighting the fact that, contrary to most thin film synthesis that we're probably familiar with, where you have sort of a reasonably good vacuum and more or less directional deposition, this is in a pretty high pressure, torr or so, and so gas flow dynamics actually matter. And so coming back to this trench, right, if you imagine gas flowing across this, the gas needs to flow down into the trench and out again in order to bring the precursors into play. And here this diagram shows flow perpendicular to the trench, but it turns out similar things happen if you're flowing parallel to the trench, that you develop these eddies in the corners. So you develop a vortex that's roughly the size of, the diameter of the vortex is roughly the depth of your PMMA. So in this case, where it's basically a 1-to-1 ratio, you have one big vortex in the middle, but as you start making your structure wider, if you've ever gone bowling with like the little bumpers in the gutters to keep your bowling ball in the middle of the lane, right? We have these two rails running down the side of our pattern that are, more or less permanent vortices, which means it's very hard for precursors to diffuse into and then out of that region to develop, to deposit rather. And so that's what gives us this tapered cross section. And so that's a sort of a fixed width set by the height of the PMMA. And so you can see this structure is about at the fidelity limit, where the thickness in the middle is sort of the bare thin film thickness, where we really have fresh precursor coming in at the base rate. And then the edges are tapering off. So if we make this wider, it becomes, basically those tapered regions are fixed width. And so you can take it in and out. And if you make it very small, then you eventually sort of suppress deposition in the middle. So that's important to understand in terms of the shape. So explains, for example, why we don't have perfect fidelity. So the black lines here show the PMMA pattern, and then you can see in the gray SEM image what's the shape of the VTC that we actually deposited. So we can do pretty good. This is something I showed on Monday as well, but just to refresh, this is now a characterization of two different arrays. In red, we have just bars. In blue, we have disks. And that's kind of a dense plot, so I'll step through it a little bit. So this is rotating from in plane to out of plane. And you see the expected sort of cosinusoidal variation from thin film anisotropy. And so for the blue here, looking at the disks, the blue data is exactly the data that I showed here, the one in the triangles, and then the circles that don't vary, where the magnetic resonance doesn't vary, is in plane. So we have no in-plane anisotropy for a disk, which is what you would expect from the shape, but it also highlights that there's no crystal field anisotropy either. But the red curves are a little more complicated. So you have sort of something that tracks more or less with the blue curve, in plane to out of plane disks and lines look the same, but in plane you have some variation. And then there are two red curves here and here. And that's because going out of plane to in plane parallel to the wire and out of plane to in plane perpendicular to the wire gives you different magnetostatics. And so it turns out we can use those fits to extract these anisotropy parameters for these VTC films, which are almost the only input that you need to predict the magnon behavior. This is why I'm dragging everybody through the mechanics of how this works. So this plus the saturation magnetization will allow you to predict what the mode structure looks like. And this is, again, something I showed on Monday, where this is now using only those fit parameters extracted from this angle dependence, extracting the expected mode distribution, spin wave distribution. And we can compare that to the blue data here, and it's easier to see in the full figure, but out to the seventh order spin wave, there's quantitative agreement. So there's no adjustable parameters in the mu-max fit to get these resonances to line up. They just line up. 1 second. And then just to remind everyone, and then these black dots here represent an analytic calculation of a cylinder with the appropriate dimensions. And that also does quite well. Yeah.
I'm sorry if you mentioned this already in your previous talk, but why is it that you only have the odd modes here? Are those the only
because
ones
it's a
that are
cavity
visible that you
measurement.
couple to? Okay.
It's a cavity measurement, and so you need the odd parity to couple to the EM
Sure.
field.
Okay, thanks.
I mean, in principle, I actually do think we're seeing the even modes because experiments are never as symmetry preserving as the underlying theory, but the calculations are more straightforward, certainly for the mu-max. So we're just doing the quantitative comparison there. Yeah.
Quick clarification. So the odd harmonic modes, does that rely on any understanding of the surface pinning?
Yes. So that's one of the other. I should have said that. That's one of the that is. I was a little too glib. So an additional parameter we have to take into account to get the mu-max to work, but it is we can set these boundaries as either free or penned, and that will shift the position of these resonances. And so when my student Andrew Franson did all this work, and it's beautiful work, but you want to nail down as many things as you can nail down. And so I pushed him on this, and I was like, well, how do other people measure whether the surface is penned? Like, let's just measure it. And it turns out they don't. Basically, they fit the model, and they do two fits, one for penned versus unpenned, and the one that's a better fit to the data, they say, now we know that our surface is penned. There are some pretty heroic measurements that one can do to measure just the surface pinning, but that's not at all straightforward. Yeah.
What would physically cause the pinning or a free boundary?
Yeah, so it's basically the materials effect that no surface is really equivalent to the bulk. So in a perfect crystal, this is sort of the background I came to from a solid state perspective. If I have an infinite perfect crystal and I cut it, then the atoms at that surface are not fully compensated, right? They have some dangling bonds that aren't being matched by the atoms that are missing from the other side of the interface. So that causes typically a reorganization of that surface where you get some distortion of the lattice. And so that distortion can change band gap, magnetic properties, et cetera. There's also potentially some chemistry at the surface. I mean, we try to keep it air-free, but maybe there's a thin oxide forming. That typically happens with thin film magnets.
If I take a phonon Bohr resonance, it'll be the odd modes as well that you see. That's so it's probably related. That's why I ask.
Yeah, whether the strength of the odd modes is related to the pinning rather than in addition to the cavity coupling. Yeah. It's an interesting thought. It's reasonable. I'd want to think about that a little bit to see whether that gives us the same constraint here. Yeah. So and again, the black is analytic calculations using the same input parameters and quantitatively predicting the positions of these modes. So we're excited about a couple of things from these results. So just from a pure sort of mechanical fabrication point of view, it's great to be able to put the material where we want it. Like that alone is quite useful. And the resonator work Greg talked about yesterday highlighted how that can be important. But more generally, what I think these results tell us is that we really can custom design a Magnon resonator. And this is not quite a unique opportunity because, and I think Georg is one of the leaders in this field. You can pattern YIG as well, and pattern it and anneal it, and be careful about the surfaces and how you treat it, and do pretty well. But this is just, I use the word facile in my title. Like this is really straightforward patterning and very accurate predictions. So this conversation about penning is actually much more straightforward here. And again, I somehow magically forgot to put this plot in today as well as Monday, but Greg showed it yesterday that like for the discs, you get exactly the same loss down to a diameter of about 25 microns as you do in the bulk films. It changes as you get smaller, but that has to do with these sort of vortex eddy effects that you're actually changing the way the material deposits. It's nothing else. So that means the surface, critically, the surface is not contributing anything to the loss of the magnonics here. So we can design a structure, we can build a structure, we can have faith that that structure will have the same line width and the same damping as we see in the bulk films. And broadly, that's I think pretty powerful. Yeah, Georg.
I would simply like to add an interesting thought at that point, because it's actually a trade-off when you make the structure smaller. It has to do with the inhomogeneous broadening. So depending on the material, so actually for YIG, if you can make the structure small without reducing the internal damping or the magnetic quality, then the smallest structures actually give you the best line width, because the inhomogeneous broadening is much smaller. So you actually have to see how small you can get without reducing the quality, and then you have a good bet that this will give you the smallest line width.
Yep, that's an excellent point. And I think one of the things that's a testament to the work Georg has done is that historically the way to make something one of these magnetic thin films small is make a thin film on a substrate. The substrate for YIG is notoriously GGG, which is not great for a number of reasons, and then ion mill, which is a very destructive process and creates a very rough surface, as opposed to the CVD, which is sort of self-assembling into these smooth structures for VTC&E, or if one is a careful technologist, one can develop techniques to sort of pull the YIG up off the surface so it doesn't interact, and sort of anneal the sidewalls and really get to this limiting regime. So yeah, like I said, they're two sides of the same coin. I think giving us doubling our materials library. When I first started talking about this, I called this section of my talk, several years ago, on purpose patterning or intentional patterning. This actually happened second. The first thing that happened was not on purpose, a collaboration with Georg's group, where we were trying to template nanowires for VTC&E. And so Georg provided these beautiful SiO2 substrates with grooves cut in them, and we were expecting to, maybe to deposit VTC&E on the top of those grooves and develop nanowires. And we grew them and then looked at them in the SEM and got something completely different from what we had planned. So in retrospect, of course, especially given the CVD, this is in fact well understood. To explain a little bit this cross section in case it's not intuitively jumping out to you, the light gray here is silicon dioxide, the medium gray is VTC&E, and the black is a void. And so there's this sort of bread loaf type shape, this ripening that happens when you grow in some modest pressure, like CVD. where the things don't just grow up, they also grow out, and then you sort of self-shadow the interior, so you have some small amount of magnetic material here and a larger amount of material here. We saw this SEM image where we're like, oh, well, that's a complicated shape that we didn't expect, but that's fine. Okay, so what we were trying to do was generate some in-plane anisotropy that we could use for sort of engineering properties. And so the first check was DC squid, in-plane, 2 in-plane scans, parallel and perpendicular to the long axis. And you know, again, another story I'd happy to expand on over coffee, but this graph took us 2 years to understand, because it's kind of hard to see, but H perpendicular is the open symbols, H parallel is the closed. So perpendicular to the nanowire is the easy axis, which is 100% opposite what your intuition would predict for these kinds of structures. And this, you know, in retrospect, a comedy of errors. In the moment, incredibly frustrating for me and the grad student working on this, where they were sure they were keeping track of the orientation of the sample, and they'd get this and be like, no, you must have flipped it. And they'd be like, well, look in their lab notebook, and oh, I didn't actually document it. I guess we'll have to go do it again. And, you know, many of those iterations until we realized, no, this is actually what's happening. And so there's actually something happening perpendicular to the nanowires here. And so this is actually the first point on this through line that I wanted to talk about that will come together at the end of the talk. So I wanted to highlight it here. Okay, and then here's a bunch of stuff going on, sort of similar to the characterization that I showed for the E-beam patterning, and just sort of stepping through how we can get quantitative understanding of what's happening here. So the top left panel is just the differential FMR scans as they come out of the system. To the right, it's integrated to make the peaks more evident. And you can see there's actually, you can see at the bottom of the scan, there's 2 peaks visible in the system, and they come together and they look like they're going to cross, but then you have this gap, and they just never cross, and then they keep going. So that's for the in-plane rotation. And then again, we have 2 different flavors of in-plane to out-of-plane. So you can come and land in-plane parallel to the wire or in-plane perpendicular to the wire. And so you can fit to each of these 3 plots. In the upper right is the fit to the in-plane, and the open circles indicate data that we've ignored in the fit because it gets close to this anti-crossing. So it's kind of distorting the angular variation. And then the 2 fits to the in-plane to out-of-plane down there. Again, we can extract all of the anisotropy parameters for this structure phenomenologically because it's a complex shape. Yeah, and then we can put that into our MUMAX simulation and try and reproduce the spectra. And so the right hand is actually a calculation of the resonance as a function of in-plane angle. And the left is the same data that I showed in the last plot. And so one of the things that I think is really cool here is that the simulation looks worse, right? The line widths are too broad. That's because if we try and simulate it with the true line width of VTC&E, we need to actually get time on the supercomputing cluster because it rings for so long that it's actually a pain. So we had to make the material worse to be able to model it, which I think that's fun. But this sort of anti-crossing behavior and the 2 peak behavior reproduces remarkably well and basically quantitatively. Yeah. I'll get to that in a second. Perfectly timed question. Referring to like a double peak here, and then I just reference you to the blue and the red lines there. So I'm just going to pick those 2 spectra, those 2 calculations, and unpack them. And it's going to be easier to see on this next slide, where the top in black is data, and you can see on the upper left there's that multi-peak structure. And the bottom in red is again the MUMAX simulation. So the amplitudes don't directly correlate, and the fields aren't quite exact. The amplitude variation is just because the mumax calculation doesn't have any detection physics in it. Right? We have to couple to our cavity, and that has some symmetries and sensitivities that mean we don't see all spin waves equally. And the small field shift, like say in the E and F lines on the left to the data, in the business of modeling magnetization dynamics, that's bang on. That's just within a few Gauss. And the really powerful thing that the mumax simulation can do for us, similar to the disks that I showed a moment ago, is you can sort of map the phase of the magnetization throughout the magnetic structure. And so something that I glossed over, this is another one of my students, Michael Chilcote, who did this work, is, this was not an on-purpose patterning. It's a very strange shape. But what he was able to do was take this SEM image and extract exactly the shape of the real magnetic material that we have and use that for the numerical modeling. And that's how and basically it perfectly predicts what we observe. And what you can see happening is that this throwaway material in the trench, that's this very thin U-shaped layer, in fact supports substantial magnon resonances. And so the two peaks here that come together and then anti-cross are essentially trench modes and nanowire modes that are sort of independently excited and have different symmetry with respect to angle. So in plane for one of those systems is out of plane for the other system. This is why they have sort of opposite sinusoidal variation. And when we get to the high symmetry directions on the right here, you can see you recover something that looks more or less like a thickness quantized spin wave mode in a thin film, which is what you would kind of expect if you're squinting at this and you miss the fine structure. You've got just a block of magnetic material. And so this is just showing the same data again and really highlighting, if I now take the data into a color plot for intensity, it really, I think, highlights the anti-crossing behavior here. And so we didn't do this at the time because we were still getting our feet wet, but it would be interesting to come back and characterize the strength of the coupling of the different magnon resonances here. You can see it's quite strong. We get a really wide gap relative to the line width. And so I was thinking about this last night, thinking about this data again, and thinking about Georg's talk from yesterday, looking at magnon resonances mediated by the microwave. This is also a magnon resonance. So it's a fun system to play with. Okay. Moving right along, because this is not a magnetism workshop, this is a quantum magnonics workshop. That was sort of a deep dive in sort of what the materials enable, which I think is an important component. But we want to operate at low temperatures if we want to be talking to quantum systems, so we should look at the temperature dependence of this. And so this is just 3 select temperatures for VTC&E as we cool it down, and you can see a massive shift in the resonance field. So this is not unprecedented, but it's unusual to see things move by that much. So, basically the first time we went to go look at this, we were like, oh, well, here's another mystery. here's another thing to uncover for VTC&E. So let's dig into this. And as we dug deeper, it got much weirder. So this is now doing the angle dependence in plane to out of plane, looking at the thin film or anisotropy. And at room temperature, that's consistent with all the stuff I've been showing you before. At low temperature, it has the opposite sign. So the direction of the anisotropy changes as a function of temperature. And in fact, there's a temperature somewhere in the middle where the line doesn't move as a function of angle from in plane to out of plane. That means that this is a completely isotropic response at that one specific temperature. So this is pretty surprising. We can map this out more carefully, looking at the total effective field as a function of temperature, and you can see it more or less monotonically decreases crossing through 0. And this is a big effect, right? So we can get negative 50% of MS at room temperature. And so this is not typical. And so we spent a lot of time trying to think about what was going on here. And you remember the seed that I planted a few minutes ago about the fact that the magnetic anisotropy for the wires is 90 degrees from what we expect. You know, what physics is happening that's oriented in that direction? Well, it's the strain of the VTC&E as it's sort of ripening off that nanowire and sort of distorting into that sort of oval shape. So we might expect also some strain to be happening here in this bilayer as we cool it down, as the substrate and the film have different coefficients of thermal expansion. And so let's think that through. So we'll just assume there's zero strain at room temperature, or we'll take that as an index strain, however you want to think about it. And if we apply a magnetic field out of plane, then one way to think about the anisotropy is it generates a space charge, positive on the bottom, negative on the top, which gives an internal demagnetizing field oriented oppositely to your applied field. And so as you ramp your applied field up and down, you have the magnetization parallel to that, and you feel your total field is the applied plus the demagnetizing field. Then when you're in plane, that space charge moves to the edges of your film, so that the dipole there is negligible. So you effectively just you get rid of that additional offset field, right? So the only explanation for what we're seeing is that as you cool things down and the crystal distorts and strains, you're introducing an additional crystal field anisotropy that's oriented in the same uniaxial direction as the thin film. And so that's present and pointed in the same direction, whether your magnetization is in plane or out of plane. And so this again was a learning experience for me and my group in dealing with these systems, in that it taught us two things. One, I thought of uniaxial anisotropy as up and down, right? It's degenerate, but in the formalism, there's a sign associated with it, and I never really understood how that could be physical. Well, this is how. Because you need to keep track of, is your crystal field parallel or anti-parallel to your demagnetizing field? And it turns out it just must be true for these materials that it's anti-parallel, so that as I systematically increase the strain, I can come to a regime where those two arrows exactly cancel out. So the shape anisotropy and the crystal field anisotropy exactly balance. The other thing that it helped to think through is, there's all these 90-degree angles in magnetism, all these cross products that can be hard to think about. And in reality, to understand all this, you really need to move to an energetics picture. Thinking about cross products and torques doesn't, well, at least to me, it doesn't provide any sort of sensible understanding of how you define what's the easy axis and what's the hard axis. But if you think about the energetics of this, you can do that. So the data on the right is just, again, the parameterized version of the 300K and 40K data. Okay, and then the final question to ask as a function of temperature is what happens to the line width, and this was a plot that maybe both Greg and Dennis showed. And since Dennis is in the audience, I will let him answer any hard questions about the model. But the orange curve represents a fit to this idea of two-level fluctuators or paramagnetic spins that are providing increasing damping as temperature goes down as they polarize. And so more of them are available to execute a spin flip. So they're more efficient at scattering magnons. And in the model, the turnaround is as you start to freeze magnons out. So YIG does this same thing, but with the peak more around 20 or 30 Kelvin. So one can fit this data for VTC&E, assuming the peak is at about 10 Kelvin, and extract some parameters there. An important caveat, though, is you notice the line width crashes back down here, and that's part of the fit. Like around 10 Kelvin, maybe that's a peak, maybe it's not, but this is a pretty dramatic shift, and this I just want to point out correlates with something I conveniently ignored the first time I talked about this, which is that data point right there at 5 Kelvin. So at very low temperatures, the anisotropy flips back. And this isn't like the sample cracking and peeling off the substrate or anything. This is all reproducible and traces back multiple samples, multiple scans. So, so we're left with a bit of a mystery that I'll let Greg solve in his discussion later on today, which is, what really is happening to the very low temperature damping of these systems. I think the fit above 10 Kelvin is good enough that I think clearly paramagnetic spins or two-level fluctuators are playing a large role here. But the very low temperature magnetism is I think complicated. Yep.
Just that the susceptibility is increasing per spin, or is it more spins?
The former. I don't think there's not more uncompensated spin at low temperature. I think at high temperature, talking in round numbers, I have exactly as many spin up as spin down. So and I'll probably get those sign wrong here. So as often we say in physics, pardon my minus sign, but let's assume that the spin down has the right orientation to flip a magnon. As I cool it, I get fewer and fewer spin up and more spin down. So I have more probability of flipping that of scattering from that magnon. That's my understanding, at least, of that curve. Is that get a yes? Okay, that got a thumbs up from Dennis. That's the right understanding.
So I heard that explanation from Dennis when he gave his talk as well, and I kind of wondered, okay, wait, shouldn't that mean there's only up to a factor of 2 difference in line width, because you go from having n spins available to deposit energy?
I'm not sure it's linear.
2?
Dennis maybe can speak to.
So the induced magnon relaxation is proportional to the difference of the population between ground and excited state. So when you're at higher temperatures compared to the 2-level frequency, then this mechanism becomes kind of suppressed. So once you deviate, you start creating this imbalance between ground and excited state, and this reflects on the increase of the line width. So yeah, and then you get something that's, if I'm not mistaken, it's a hyperbolic tangent, and
so you're saying it's proportional to the difference and not the absolute number of available spins. So it's not a phase space argument. Is this equivalent to some kind of motional averaging effect?
So motional narrowing, I think, when I think about motional narrowing, I think more like you're going from Gaussian to Lorentzian type of like broadening due to the characteristic time of fluctuators. Not necessarily. So I think I don't have expertise on the motional narrowing with respect to the line width, only with respect to like coherence T2 of the, and here we're actually calculating T1. So
I think Mike has a question.
So what is it about the fluctuators that leads to this 10 Kelvin? Is that
the characteristic energy scale
okay, so
in the model?
Their spin splitting, essentially.
Yeah, I think that's right. And then with the asterisk that we're not sure if 10 Kelvin is the right number. Because our data has this additional contribution that we don't necessarily understand. Yeah, but yeah, that's what the model does. Greg, did you still have, or did we cover it?
I had a comment about emotional narrowing, but I think Bill so whatever I say is irrelevant. Motional narrowing, I guess, in my way of thinking about it, the rate is very important, right? So in motional narrowing, it's like it's not just the number, but it's actually the rate of the of the motion in this case, right? And so I think that is an interesting comment because there is a rate involved in this, but I don't think motional narrowing is the right picture. But I think it might be that you could make a connection. I'm not sure. So
just to give the physical picture. So to calculate a T1, dumping into a system of two-level fluctuators. Two-level fluctuators fluctuate, right? That's the F. So they're fluctuating up and down, and as a function of temperature, that fluctuation rate can increase depending on the mechanism. And if that fluctuation rate, that generates a correlation time for your environment. If that correlation time becomes shorter and shorter, then the rate for decay becomes shorter and shorter. It's just proportional to that. And so if you have a faster and faster fluctuation in these two-level fluctuators in your environment, generically you get this kind of behavior. So I guess it's consistent with motional averaging, but it doesn't mean that it's included in the theory.
Let me just comment on this. What you said is exactly what's happening for temperatures lower than 10 Kelvin, correct? Because the TLS, in principle, they're not in resonance with the magnum. Okay, so you need broadened TLS to be able to have this conserving energy excitations of the two-level system. When you go to temperatures lower than 10 Kelvin, the TLS, two-level fluctuators, two-level systems, they become not very broad, and then the magnets are not able to excite these impurities anymore. So that's why you get this like abrupt suppression of the line width, just because the magnets are not destroyed anymore.
I have one question. What is
this one here? Okay. So regarding the same discussion, so in this kind of two-level system damping, we have two contributions. One is due to longitudinal interaction of the magnetization with two-level systems, and another one is the transverse interactions, right? So this kind of peak structure comes from the longitudinal interaction. And then we have, due to the transverse interaction, we have again, you go down and then you go up again, right? So I wonder if you observe that going up as well.
Yeah, so, and I think this is the model that has been developed for YIG, and something we're explicitly interested in exploring, because the coefficients on that model are very material dependent. Like how many uncompensated spin, what's their character, what's the coupling strength to the magnons. And so unfortunately I don't have a clean answer for you. We're definitely exploring that space. And maybe Greg in his discussion might allude to some of this, but there's we're seeing some complicated behavior that we're still trying to understand. So maybe yes, but yeah, but we can't say anything definite yet.
Right.
My question was usually from these type of experiments, you can work out what paramagnetic what is the paramagnetic impurity or parasitic resonance it's causing this. Can you know?
To chemically identify it?
Yeah, to know what it is. Is it some sort of defect in the?
We don't know chemically. I think in Dennis's model we assumed spin 1/2. I think from the magnetic resonance that's the best we can get, right? And which is not terribly informative about where those extra electrons are coming from. Whether it's, as you say, a point defect in the VTC&E or some impurity. My suspicion is it's uncompensated spin in the VTC&E due to some point defect, some missing vanadium-nitrogen bond that goes away.
Can't you do some form of spectroscopy to try and determine that?
ESR spectroscopy, or you mean optical spectroscopy?
Oh, if it's paramagnetic, it should be a microwave. You know?
Be happy to talk about that. We didn't do an intensive search as part of this study, which perhaps we should do. But generally, we did not see other resonances. Seeing like an ESR line as well as the FMR line that we could then explore the spectroscopy of the ESR line to find its local coordination and give us some hint about what it is. Part of that is because the FMR resonance is so strong here that we're typically operating at very low powers where it would be hard to see an ESR signal from a sample of this size. So it's a good suggestion to maybe revisit some of this and go to higher power, ignore what's happening to the FMR, and see if we can find some ESR signature that might give us some idea of what's happening there. I will say a potential complication is sort of some spin-magnon coupling that might muck around with what the ESR looks like, but we'll see. I think there's a question in the back.
So you stressed the analogy to the YIG case here. So
yeah, that's at least the model.
They're basically the peak position in temperature that gives you a ballpark estimate about the energy scales of the fluctuator we're talking about.
Yeah.
So my gut feeling is, given the fact that I would read off there 20 Kelvin, this is round about terahertz or so. And that makes spectroscopy hard. Because the damping mechanism, so and I might have misunderstood Dennis how he calculated or estimated, is that this damping mechanism works nicely if you have a decent population differences in the defects you're talking to. If you're higher in temperature, they basically wash out because they become evenly populated and then saturate thermally. And if you're lower in temperature, they also kind of drop out of the picture because the transition which you need to drive there is not thermally there, so you don't have the energy. So, and this was my very simplified picture that I kind of developed for YIG there, where rare earth defects kind of are typically associated or identified as origins for this peak.
That's an interesting point. I have a question about about what that frequency scale means. The question that I thought Mike was asking, I thought I was answering, was sort of a spectroscopic measurement of the which would be an ESR frequency, which would definitely not be in the terahertz for any sort of reasonable size spin. That's a different time scale potentially than the fluctuation frequency, the spin flip time, which I haven't thought about, but I could see being in that terahertz frequency range. So maybe just first as a question, so is that your understanding of the physics that we're talking about here, as I just described it? That the terahertz is the fluctuation frequency, not necessarily the resonance frequency of whatever the spin is that you're coupling to?
So I want to stress that I'm not a super expert on this. So I personally find it annoying that there is a peak for YIG.
I think you're not alone in that.
And I just looked at the old textbooks there, and there are kind of these, for me, hard to understand pictures where they argue that basically they kind of discussed or identify the defects which are behind this peak by looking at the temperature peak, whether the damping peaks, and then they have some argument that this kind of couples to the spin system in a very off-resonant fashion, and that you basically, so what you need to do at the end of the day to create damping at this temperature is you need a mechanism which allows you to dump energy.
Yes. Yeah.
And these fluctuators need to kind of fulfill certain criteria in terms of that they can participate in this, and you can freeze them out or you can oversaturate them, and that makes this peak formation. And this was kind of my very simplified understanding.
Okay, so
I bring it to you.
Yeah, so maybe Jevin and then Greg.
Yeah, so relating to kind of rare earths being the fluctuators that cause problems in YIG, I mean, we have maybe a situation that's quite analogous with our gadolinium vanadate as we're cooling it down, right? So at room temperature, you put your gadolinium vanadate sample in your microwave resonator, and it doesn't change the Q at all, right? It's full of spins, but because of the fast spin lattice, this is our picture now, because of the fast spin lattice relaxation, the line's so broad that it you know, the sort of the optical depth that's at your frequency that you care about is kind of zero, right? And then we see very much this picture as you cool it down, and our argument for that is that you know, these things are getting narrower and narrower and narrower. You know, they're still broad compared to the 10 gigahertz resonator frequency, right? So as you make the thing narrower, things get worse and worse, right, in terms of your line width. And then, but eventually they get narrow enough that they become off resonant, right? So, I mean, maybe this was the point. Maybe the 10 Kelvin doesn't have so much to do with the frequency at which you freeze things out, but it's more the point where your line width is optimal for causing destruction, right?
Yeah, no, that's a really interesting point. Before we jump to Greg, I wanted to point out another piece that I think, not for the data set here, it's maybe too high temperature, but as one moves towards still fridge temperatures, something I'm curious about, I don't know that, and Greg may talk about this in his guided discussion, is that there's also the coherence time of the defect spins to take into account. Because eventually, if those, and the magnons, right? So if those times get to be long compared to the scattering time, then you can have an additional effect where everything just synchronizes. You know, in my mind, I think of it as the magnons recruiting the defect spins into the magnon, right? If everything's super long-lived, then you only have to scatter once, and then everything's in sync for a long time after that. And that also could show up in a reduction of loss, because you're still coupled to the same bath, but that isn't a lossy interaction anymore.
Just a minor point, and I'm going to rehash some of this, so please feel free for more of the same this afternoon, and you can just shout me down. That's fine. But just reminder in a couple of points. So in the paper that you guys published with Dennis, I guess Michael and Dennis identified the fluctuator energy scale to be around 1.2 millielectron volts. So that is indeed kind of a much higher frequency than a typical EPR accessible state. And they speculated that it was some sub-gap state in the VTCD. Maybe Dennis can say more. And then in YIG, the number that I've seen thrown around in the literature is like 2.5 millielectron volts, so which indeed correlates to the higher temperature. So I don't know that this fit is a complete description, and the models are a complete description of everything that's going on. But I do think that people have concluded that it's the actual energy that's corresponding to the temperature that it's high, and not just the fluctuation rate. But the fluctuation rate is temperature dependent.
That's an interesting question, and I'll say, just, you know, pulling the cover off, you know, among friends in a workshop, Line width is particularly tricky parameter here because at a minimum we have spin wave modes, and like the n=1 spin wave mode and the FMR mode are very close in this system. We may have other peaks from other things happening. So the difference between broadening and peak splitting can be hard to resolve in certain regimes. And so there's a lot that can be happening, which is why I've been a bit cagey about saying too much about what's happening in the low temperature and even below. I mean, I think if we start here and move up, the fact that we see the damping increase, that was perhaps my phone. I think that all makes sense within this fluctuator model, but whether that peak is indicative of the energy scale is an open question. I think we said it right in this paper that this is the model that we have for understanding low temperature damping. So if we fit this to this model, these are the model parameters that come out. Not meant to be a categorical statement that this is all the physics that's happening there. So I think Georg has a question.
Very simple question. I'm just looking at the numbers here. So this is not a sample with the optimum line width that you showed at room temperature. What if you start with different line width at room temperature? Does it somehow go proportionally, or does it always go up to 15? Or how does it behave?
Good question. I don't know that off the top of my head. We saw quite similar behavior across multiple samples. Well, I wouldn't want to tell you the wrong answer about whether other samples go to 15 or 12 or 19. And we're not. So also I should point off, my student chose to plot this so that 0 is not on the basis here. So you're right, that's not perfect, but that's within a factor of 2, or maybe 50%. So I can definitely look at the data and answer your question, but I just don't remember off the top of my head. It's a good one to know whether, yeah. Was there another question? No. Okay, so let me pause here for a programming discussion. So I think we're already past my nominal time. I have some other slides of new results, but I also don't want to stand between people and coffee and snacks. So there's a.
So this discussion is very much along the lines of what I was imagining that I was going to talk about. Not complete, but so what I would suggest is that if you want to present the new results, which I think we would all love to see, you could start the session at 2, present them, and then, I only have like 15 or 20 slides, and it's mostly just to get discussion, and then we can take up as much discussion on this stuff as we want, but that way, we don't want to miss your new results, right?
Yeah, I don't want to oversell the new results. So, as you could probably all just hear, and as we talked about at the end of my earlier presentation, I'm just going to give a couple more slides, and then we'll see where we're at. Maybe turn the floor over to Greg, or think about what makes sense from the programming there. And so I just want to do two last things. So the first is finish this story. I only got to 3 of my 4 vignettes about strain, and then I have some new data. And a benefit of Carlos's flexible structure is I advertised it at the end of my the morning session as new data. In fact, my graduate student got me updated plots after that talk. So it will be new data that we can talk about, which means I really won't understand what's happening. But so just to reboot, we had a long discussion about the meaning of this, excuse me, or the meaning, the origin of this line width change. But the thread I want to pick up is from this plot, which is where we were able to tune the total effective magnetic field seen by the system, or the effective magnetization, depending on how you want to group your terms. And I talked about so in this low temperature paper, we posited the existence of a magnetocrystalline anisotropy, which just so happened to be parallel to and in the opposite direction to the shape anisotropy, which allowed us to do this kind of temperature-dependent tuning where temperature is effectively a stand-in for strain. And is there a microphone for?
So on your diagrams, you've got pluses and minuses. Are they monopoles?
Yes.
Great.
Yes.
I love
that.
that.
So this is sort of a convention of magnetism of imagining your dipole as a space charge, because we're used to sort of understanding how pluses and minuses work for the electric field. If you hypothesize the existence of magnetic monopoles.
Yeah, but they can be fictitious, so it's no problem.
Yeah. They're totally fictitious, but they're there to sort of guide
I'll just
your
say
thinking.
I've done experiments in the lab where you rotate a magnet, and you can calculate the EMF that you derive from those monopoles as an effective magnetic current, and you get the same as a Lorentz force.
So that makes sense because
yeah. So my question is are the fictitious monopoles true, or the Lorentz force?
That's a deep question.
I'm doing these harebrained experiments in the lab, wondering about this.
That's awesome. And if you think this system would be useful for that, I would love to talk to you about contributing.
I was wondering about that in the past. Like, so surely it wouldn't be, some theoretical physicists would die seeing that, but electrical engineers use these impressed fields and affect fictitious things all the time. Yeah.
Yep. And so since we have our banquet dinner tonight, maybe over a beer, we can dig deeper. Okay, so with that reframing, then what we did next, which is sort of what conceptually you would do first if you want to explore strain, is we built a system where we just bonded a VTC&E film to a piezoelectric wafer, where we can control the strain in ways that are controlled and understood, rather than relying on some sort of self-assembled structure that just sort of builds itself with intrinsic strain, in the nanowire example, or in the temperature dependence, where we're using temperature and the difference in coefficient of thermal expansion to put in the strain. We'll just use strain to put in the strain. And so this is what the structure looks like. We do characterization versus field and frequency, showing just basically that the film is a standard VTC&E film. We don't do anything terrible to it to get it here. And just the first sort of is it there test shows that in fact, as we apply a voltage to the piezoelectric and introducing strain to the film, we get a significant change in the FMR resonance. And so I put these slides up on Monday. For those who may feel like a bit deja vu, but just to talk through it again. And then in this stack here, and I apologize if some of these axis labels are a little too small to read. I couldn't figure out how to fit this bigger on the slide. But in the top, we have basically the resonance frequency tuning as a function of applied electric field. Critically, the total line width, the inhomogeneous broadening, and the alpha do not change. So we can strain it and nothing bad happens. And we did like a first order failure analysis of a few hundred cycles. Didn't see any change there either. So it's tunable and gentle or reproducible, however you want to think about that. Well, it's not actually squishy. It's just we're not cracking it by stretching it. because that's one way in which you can induce changes, is introduce microfissures and defects, and not even macroscopic cracks, but like threading dislocations or something that would propagate. We don't see any evidence that that's what's happening. Yeah.
How does the electric field translate to strain in your film?
Those numbers are in the paper. I have a table in the next slide that will maybe get us to there. Oh, you have those numbers off the top of your head?
I don't have the numbers, but I can say the strain is right because it's the only part that I had in this experiment. So what was done is
I think the emphasis in that sentence was perhaps meant towards the beginning.
Yeah, fair enough. But what I'm saying is when he plots the strain, it's accurate on the VTC&E. It's not just saying, oh, the PMNPT changes, and so we assume that's the strain in the film. It actually is the strain in the film. And I can explain the details if anyone cares, but it is the strain in the film for certain.
Yeah, so we worked with Greg to get a sort of a quantitative measure of exactly the distortions that we saw. The reason I say it's not squishy is one of the many things, or not terribly squishy, one of the things you can extract is the magnetoelastic coefficient and compare that to YIG. But more interesting is this table, which compares things on many different axes. And so the red lines I underlined are for a representative VTC&E sample and terphenol D, which is sort of a famous magnetostrictive material. And so just looking at these columns, you can see NS is dramatically different. We have 10,000 versus 100. So that's 2 orders of magnitude. And really emphasizing when Greg and I have both been talking about that the M sub S for VTC&E is small. It's really, really small for almost any magnetic system. And then if you look, the conventional figure of merit here is this magnetoelastic coefficient, which is about 1 for VTC&E, about the same size for YIG, with some sample variation, structural variation. And again, 2 orders of magnitude or 3 orders of magnitude bigger for terphenol D. So by most conventional measures, it's not even close. So basically there is no magnetostriction in VTC&E compared to this world champion compound. But what we argued is, we're not trying to make a mechanical actuator out of this or something. We're interested in gaining local control of microwave properties. Like that's the regime in which this is interesting, potentially for quantum, potentially also just for sort of more conventional microwave electronics, is sort of everyone's wish list in the field of magnetism is it'd be really nice if we had an electric knob that we could turn to change our magnetic properties. That's just generically very challenging to do. So for that kind of functionality, we actually have, we introduced this new metric psi, which is effectively how far the resonance shifts as a ratio of the line width. And by that measure, VTC&E and YIG are comparable and comparable to terphenol D. So you might I might think of this as functional magnetostriction. So what's magnetostriction that we can do something with for applications, at least within the space that we're interested in? Yes.
Just briefly on your last transparency, you had a comparison with something like 10 to the minus 4 for VTC&E and 10 to the minus 6 for YIG.
Yeah,
so what number was this?
That must have been a typo because they're comparable here. Yeah, this is the danger of pulling up slides from the dim past and dropping them in at the last minute. Yeah, I saw that as well, and I was like, well, we'll just hope no one noticed, but I should have known better in an audience of experts. But so this is also not quite the strain value, sorry, and again, apologies for this is a paper that I haven't looked at in a little bit, unless alpha is the strain. No, that's, oh, duh, yeah. Yeah.
Sorry. Magnetostriction coefficient is kind of, in some sense, a strain susceptibility. So you've already divided it out.
Yeah. Oh, yeah. But I was just trying to get to the specific question about how much is the strain. And again, the numbers in the paper, I apologize for not remembering it, but one way to think about it is, the field scale that we explore here is basically the functional, most of the full functional range of what you can do with PMMPT. So you can't strain it much more than this. We took it effectively out to the rail. So if you're used to working with the system, one could probably turn that into a ballpark for the total strain that we're introducing. But one thing to note, and that's kind of fun, is you can compare that frequency shift sorry. Oh, look at that. How clever of me. Yeah. Yep. So around 10 to the minus 4. But looking at that slope from that top graph, well, I'm just going to finish this thought so I don't sound like an idiot, and then I'll take Dennis's question. And come back here, right? There's a slope there as well. And so you can look at the change in resonance frequency from applied strain and say, okay, well, so how big a temperature difference would I need on this graph to get an equivalent change? And then ballpark comparison with the difference in the coefficient of thermal expansion as sort of a cross-check between the two measurements. So the reason why that can't be directly quantitative is we don't have directly a measure of the coefficient of thermal expansion for BTC&E. It's just not been measured. But we use numbers that are sort of ballpark for similar systems, and there's actually not that much variation in that number across similar materials, and all of that sort of makes sense and checks out. I think I was just going to ask whether you can relate. Okay.
You just answered my question. I was just going to ask whether you can relate the temperature dependent strain to the strain you guys applied. So. No, sure, yeah, but he said that they did not relate that yet.
Like if I did that in Sapphire, permittivity and strain dependence, and I think the temperature dependence was an order of magnitude more than the strain or something. I can't remember exactly, but
yeah. So the strains you can apply by making it cold and taking advantage of the difference in thermal expansion coefficient is much larger than you can apply with the piezo. Yeah. So the piezo is just in that sort of upper range. And like the simple benchmark is with temperature we can go through 0, and we're nowhere near that with the piezo. So this is normalized as a shift from equilibrium, but it's about a 40 megahertz shift on a 10 gigahertz line. So it's a pretty modest change. I think Georg has a question.
Yeah, just, I mean, you showed that you can shift the resonance frequency by applying strain, but on the other hand, when cooling down, you basically changed the anisotropy. So is this directly related, or did you check whether you have a change in anisotropy there? Certainly you would observe it as a shift, but did you check also the perpendicular and in-plane shift?
Yes, I didn't clip out that from the paper, but we do the full angle dependence and fit to extract 4 pi ms and get comparable numbers. Yeah, and that in itself doesn't make sense. Strain shouldn't change ms, but what it's doing is it's changing the anisotropy, the crystal field anisotropy, which remember is fighting with the shape anisotropy. So it's changing the effective value of ms that we see in the system, or the H effective. Yes, exactly, yeah. Okay, so then coming back full circle, so this is a paper I didn't talk about today, but talked about Monday, which was a combined study. Yeah.
Sorry, maybe one question related to this. So are you Did you check if this is a G approximately equals 2 system? What is the G factor of this? Is
of the FMR?
Of the FMR?
It's pretty close. I mean, the MS is small, so the Cattell equation, the difference between that and a pure G equals 2 is modest, if that's what you're asking.
Yes, I'm asking because I have only seen now angular dependent measurements as function of temperature, basically. So if you only have one frequency, then if the G factor would change as function of temperature, then the analysis is more complex, because then it's more difficult to disentangle basically MS anisotropies and all of this. And this is
if I understand what you're saying, using the language of sort of G tensor anisotropy, which is sort of the ESR language for talking about the crystal field effects. Yes, that's in fact exactly what I'm talking about here. So the orange arrow is effectively the G anisotropy, the crystal field anisotropy that turns on. And in fact, we can't, you'll notice I've very carefully not given you a value for the size of that field, because we only ever measure the sum of these two. So I can tell you the change, but I don't have a good, and happy to take suggestions, but we were not able to think of a way to provide an absolute reference, a fiducial point for the size of that anisotropy field. That's exactly right. This is sort of the cartoon representation of some very nice DFT work coming out of Michael's group that's supported by electron energy loss measurements done in a TEM, validating the electronic structure. And I talked a lot about how the various levels work on Monday, but here I just want to focus on the fact, on the symmetry, that what this DFT model identifies is that there are 6 TC, if we take a vanadium-centric view of the material, so this is not quite a unit cell, this is bigger than a unit cell, but conceptually I think this is the easiest way to think about it. So we look at a vanadium, there are 6 TC&Es coordinated to each vanadium. 4 of them are identical and in plane, that we've labeled equatorial here. And then 2 point out of the plane, which are labeled apical. And so the green and the blue color code corresponds over here, and this is, this was arrived at after all the science that I just did, just because that's how science happens. It comes when it comes. But this now retroactively gives us a physical basis for understanding where a uniaxial crystal field anisotropy might come from. Right? Clearly, the out of plane direction is very different from the in plane direction in terms of those vanadium spins. They're gonna be seeing different environments, talking to different vanadiums and with different, or talking with different TC&Es, excuse me, and with different energy structures. Was there a question?
Yeah. So, how are your crystals, when you grow them, oriented?
Yeah. So something else I've carefully not brought up. This is definitely not a single crystal material. It's I would think of it as polycrystalline with a very small grain size, if you want to be polite. If you want to be rude, you could call it amorphous. But if it's amorphous, I think it's amorphous in the sense of like amorphous silicon, which does still have a local crystal structure, so you can verify that. And certainly the calculations bear that out, right? That's the energy structure that we see, and there's it's a bit challenging to get structural information out of the system for a couple of technical reasons, but we're quite confident of the local coordination. And I think you can see that in some of this EELS data, where you can measure that there is, carbon-carbon bonds, carbon-nitrogen bonds, nitrogen-vanadium bonds, and that the vanadium has octahedral symmetry. So we're sure we have the crystal structure right, but those crystals are not necessarily uniformly ordered. What I suspect we were seeing in the nanowire case, where we identified a unique strain axis, as well as in the thin film case for temperature and with the piezo, is that I think as it grows, we have at least sort of pneumatic order, that the different grains probably typically tend to orient with these planes of equatorial TC&E all lying in the same direction. And that's what gives rise to this orange arrow on the previous plot. Yeah, I think Mike has a question behind
Do any of the vanadiums exist with free electrons?
Not that we can measure. I mean, that's not these measurements are not super high fidelity, right? You're looking at sort of XPS type peaks, which have some noise on them. We don't see any indications of other oxidation states. But we do, as we talked about this morning, see evidence of two-level systems, though. So, for example, a vanadium 3+ could be contributing to the loss, and we might see it that way. So, final slide. Just to, I guess I condensed my vignettes patterning into two. I should have had 4 images here, but this is sort of the trajectory that I was trying to show. Just because, I mean, lots of great information about VTC&E that we've been talking about, but just also I think it's a nice story in kind of describing the arc of how science happens. Right? You see a hint here, you see a hint there, you try this measurement, you try that measurement, and eventually you collect enough information to sort of stitch together a narrative that's self-consistent and that's explaining what you're seeing. So this is the pivot point where I was going to break and start talking about new data. So if anybody has any remaining questions here, this is probably the time. Yeah.
So giving you a temperature control of the uniaxial parameters, would you say that at low temperatures this becomes perpendicular magnetic PME? Or has a perpendicular magnetic anisotropy, so it goes out of plane if you're not forcing it by an external magnetic field?
Yeah, it absolutely does. Sorry, it took me a second to translate that, but this negative H effective means out of plane is the easy axis.
Thank you.
Yeah, and so you can also see that here, whereas we rotate the field, we get a shift to lower field for the resonance. Yeah. And also, just to be a bit pedantic, we are indeed, the variable we have under control is temperature, but I would think of it in terms of strain tuning. It's not inherently a temperature effect that's driving that physics. I think it's the strain between the substrate and the film, which means that it's not the best control parameter. Sample to sample, you can have modest variations and how that works depending on what the interface looks like. Yeah.
Maybe another question in this direction is your strain setting. Is this an uniaxial stress that you apply to your system, or is it a biaxial in-plane stress?
It's being applied in plane.
Is it basically stretching this in both directions, or is it uniaxial?
Both directions, and I think this is what Greg's results show. So to not make it unnecessarily mysterious, what we did was, turns out you can pattern VTC&E by heating it with a laser spot. So he effectively burned a couple of fiducial spots in the film and then applied the strain, and you can look at just look where the spots move, and you can directly measure it. And so that was sort of a biaxial in plane distortion.
Thank you.
Okay, so these are the very, very new results, And so this came out of a project with Greg's group where we wanted to start looking for nonlinear effects in the Sewell instability. And so there's the proper careful way to do that in a dill fridge with superconducting lines and whatnot, which is powerful but time consuming. In the meantime, my graduate student, Rob Klassen, was like, well, we have the room temperature EPR system. Let's just turn up the power there and see if we can get into a nonlinear regime and see what's happening. And absolutely something happens. So this is a pretty big effect. And notice the field scale here. This is 2 Gauss. So these are already very sharp lines. And then something even sharp on that scale popped up. And so this is the teaser. This is why we think it's interesting. And I want to be clear up front. This is definitely work in progress. So I'm not going to end this part of the talk with a punchline of we know exactly what's going on. I think we are developing a working idea, and I'll walk through that. But let me start with just sort of the systematics. So this is one of the less exciting but more important plots to show is that at these high powers, if we rotate the orientation of the DC field, we see the shift in resonance consistent with sort of the anisotropy. So anytime you see something very sharp like this, one candidate is in, we've done something terrible in the microwave engineering aspect. Maybe so there's some like weird reflection or something happening. This is a commercial Bruker expand EPR, but things break. But this tunes with the FMR resonance, so we think this is something intrinsic to the magnetism. It's not a pure microwave effect. So that's an important sanity check before we push too much further with that. So then, of course, the next thing to do is take data at a lot of powers, and so that's the plot you can see here. It's hard to resolve any details in this version of the plot, but just showing that the main purpose is to just show there's sort of a smooth evolution as the power turns up, and when this feature appears in the middle, you see the 2 peaks of the derivative curve, the maximum and the minimum, the derivative of the Lorentzian move further apart. So there's some broadening effect as well. And then this is kind of the last piece of systematics is plotting the onset of this feature as a function of the AC field modulation that we're using to do the measurement. So this is a longitudinal modulation at relatively low frequency that's just standard for magnetic resonance for improving your signal to noise. It was why we get a derivative response instead of an integrated response. And you'll see at very low frequencies, the FMR intensity is following a linear shape. This is plotting square root of power, so linear with power, and not much happens. But once you hit 30 kilohertz, you start seeing these divergence, and I'm not showing it here, but basically at these points where the curves split away from this sort of linear behavior, or would be linear on a linear scale, is where we see the emergence of this additional sharp feature. And so it seems to depend on the frequency of this longitudinal modulation in a pretty strong way, and it gets lower power with higher frequency. And so we were looking for a Sewell instability. This is not, we think the systematics are not right for that. Our second guess was, well, maybe there's some paramagnetic spins and we're seeing some sharp feature. We're now pretty convinced it's not that. Some of you may already have thought of this being more expert than I in magnetic resonance. This is an effect. This is a paper measuring very similar looking data. So we think this is significant in EPR. I think this is anthracite in this paper. And in the top is sort of the FMR response, and in the bottom is the reflected power. And the columns represent successive cavity loading. So they start off with a little powder, and they add more and more and more and more. And as you add more, you end up with this bistability. And effectively, I think what's happening here is first, EPR has very sharp line widths, comparable to VTC&E. And so if we want to think of that as a queue, the EPR queue and the FMR queue for VTC&E are both comparable to the queue of the microwave resonator that we're using for the measurement, a few thousand. So that's a recipe for the strong coupling regime, which we've been hearing about for the last couple of days. And then, so as you pump, so either as you pump harder, put more microwave photons into the cavity, you can drive interactions, or as you add more material. And so in this experiment, they're adding more material. In our experiment, we're turning up the microwave power and just using the same size sample. And I think, and now we're getting to where the ground will progressively get shakier and shakier under my statements as we move forward. I think of this as sort of an anti-crossing in the Magnon resonator system. And this bistability is sort of hopping between those two different modes. And the special sauce at the end here for this modulation is that the reason why we think we're seeing this bistability is in the control algorithm for the EPR system, there's an automated frequency control that dynamically tunes the frequency in the cavity. And so it's hopping between these two sort of metastable states of sort of Magnon microwave photon interaction. Yeah.
Just to say, we saw something similar in a optomechanical system with hysteresis, with hopping, and there's a definite signature if you sweep up in frequency and down in frequency.
Yes, so that's here, and that's exactly the hot off the presses data that I got from Rob from this morning and now. Like he actually had this and just had neglected to let his advisor know until I told him I was going to talk about it, and he's like, "Oh, you should look at this." And so this is at two different powers, and sort of, you know, at the highest power in particular, it looks a lot like those curves that we were seeing in the EPR data. So I'm now reasonably confident that we've identified the phenomena, but what we haven't really thought through is what can we do with this? You know, what is there something about this that we can use to learn about the VTC&E material, about the Magnons? I mean, in the EPR community, they use this as a way to quantitatively count the number of spins, basically the cavity loading fraction, which is useful. If that's all we get out of it, that's nice. But I'm a little curious about this broadening that kicks in. You know, if there's something that can tell us. Maybe it's just telling us that, you know, essentially microwave cavity physics works like microwave cavity physics, and there's nothing particularly new or interesting there in that direction. But at any rate, I figured this is the community to share this data with. If anybody is going to have some good suggestions, already reassured to hear that Mike has seen something similar. So we're not totally out to lunch in this interpretation. Yeah.
I'm just looking at the paper that we published, but it's very similar.
Yeah, if you wouldn't mind emailing me a copy of that paper, that would be great. Love to look through that. Yeah, so not expecting any dramatic insights on first contact with the data when I don't even, you know, necessarily have the foundation to lead you, but I thought I'd plant this seed, you know, maybe over the next couple of days. If there's anybody has any insights, be happy to chat about it. So I think I've taken up a lot of time, so that's probably enough of me monologuing. So then I guess there's a programming question for Carlos and perhaps a democratic vote. I guess, Greg, you have some more line width discussion.
about line width, and we can keep it short. And what time are we done with this session? It's like 20 minutes, right? Oh, well, we just
Okay.
we'll
So-
probably run out of time, or maybe people will fight with each other over line width, which would be great. So yeah, let's just move ahead.
All right. Well, I will turn the floor over to Greg then.
Give me 1 minute to set up. Maybe 2.